Ashiana, and I am in Broward College. I am in Professor Makey Manchola's Friday evening Abstract Algebra class. He gave us a proof to do on video, and the problem that I have chosen is not in the Contemporary Algebra book, but a problem that the professor presented for our homework. Out of the two numbering systems that we were allowed to use for our video presentation written part, it is number 2 in both of them. And today we are going to talk about this. Consider the structure of the complex numbering system, -0 under division. Is division a binary operation on the structure of complex numbers -0? Well, the first thing I have to say is, of course it is, because to be a binary operation, just have to have two operands. I believe that you'll find it's closed on the complex numbers -0. And if you were wondering, however, the structure does not form a group. There's an identity, which is 1, and everything has an inverse of itself, but the operation isn't associative. So let's talk about this problem. Complex numbers are written in this form. So we're going to let a plus bi be a complex number. We're also going to let c plus di be a complex number. Very, very important to know here is that a, b, c, and d are all not equal to 0, -0 here. So took the 0 out. Since we want to know about division, let's divide these complex numbers. I'm going to take a plus bi and divide it by c plus di. Now, in order to make this a workable problem, we're going to have to multiply the denominator by its opposite or its conjugate so that we can get the imaginary number out of the denominator. In order to do that, we're going to set the problem up something like this. To multiply by its conjugate would be c minus di, and we have to do the same thing to the top that we do to the bottom so that it is considered 1 and doesn't change the problem in any way. Now when we do that, multiplying by the conjugate, we get a difference of 2 squares on the bottom. That comes out to be c squared minus d squared. Now the top is difficult to multiply and long, so we're going to take our time with this. Instead of foiling through and talking about it, I'm just going to write the answer. Because of course FOIL is first, outside, inside, and last. So AC is your first, and then your next term, like I said, I'm going to write it out, ADI plus BCI minus BDI squared. Now let's simplify if we can. We know we have a difference of 2 squares on the bottom, c squared minus d squared. And on the top, we can simplify AC plus BDI plus BCI no, I'm writing the same thing again. I can simplify into AC plus BD plus BC minus AD and take out the I. That's in factored form. That's correct. Now, let's simplify even further and break these down into two separate fractions. AC plus BD over our difference of squares plus BC minus AD over our difference of squares with the factored out I. Since we come up with these two normal numbers, if you want to call them, at the end, not complex numbers, times I, division is actually a binary operation on the complex numbers, taking out 0. That's it. Thank you for your time, and this is the end of the proof. Bye, Professor.